these conceptions came from high energy physics. So nowadays we observe some interaction between this very tight interaction between these two fields. And I would like to discuss another one important point for both these fields. This point concerns the mass generation for particles in quantum field theory and gap generation in condensed matter physics. Mainly, my talk will concern a special point for this mass or gap generation connected with magnetic field. Sometimes in quantum field theory we already have mass generation which requires some special conditions. Among them is that you can form quantum state when your coupling is rather large, say larger than some critical coupling. And then if you, what I would like to show is that when you switch on magnetic field, then you have mass generation at any coupling constant. That's why we call this mechanism as magnetic catalysis, which was elaborated in the 90s by our group, and even this term magnetic catalysis was by our group, was introduced actually. So my plan will be the following. I will start with simplified BCS model, because this is a model which actually inspired mass generation in quantum field theory. Then I discuss mass generation in a generalizing model, quantum electrodynamics, magnetic catalysis, so apply magnetic field. Then I come to Dirac theory of graphene, QED form of graphene. I discuss gap generation in graphene and magnetic catalysis. So this is my. So let us start from this simplified BCS model. Very simple Lagrangian. This is local. Simplified means that I use local iteration in G is coupling G to electron phonon interaction. So this Hamiltonian has U1 symmetry, phase symmetry, and if you know gap equation for the order parameter, which just condensate of electrons with spin up and down, has the following form. It's weight in the range of energy bounded by the frequency. It's easy to see that non-trivial solution for this equation exists at any small coupling, but what's very important is coupling. This is formula for the gap. So, but besides coupling constant, we see here the presence of density of state on the Fermi surface. That's very important. So we see that usually the dose as function of energy behaves like square root of energy. So, for example, at zero energy it vanishes, but here we have dose at Fermi surface. So, for example, if delta is zero, so neglect this delta numerator, then we find all this expression, and delta we need to cancel this pole. So as a result, U1 symmetry is spontaneously broken. But if Fermi energy is zero, what is usually we have in quantum field theory, then it's easy to check that solution, non-trivial solution really exists, but it requires some more strong coupling. which is greater than critical one defined by this formula. Now let's come to famous Naukova model in quantum field theory, which was invented by Naukova and Giovanni Giovazzini in 1961. As I already said, this model for one generation particle physics was inspired by BCS theory. Originally it was invented as some theory for nucleons, because at that time nobody knew about quarks or gluons and so on. But what is interesting is that in the 80s this model was again rediscovered as effective low energy model for quarks, because this model doesn't have a phenomenon of confinement in it. But what's important, you can find bound states from quarks, hadrons, introducing some phenological parameters. You can even estimate masses of bound states. Actually, Nambu won his half of Nobel Prize in physics just for this model. This is formulation of Nobel Committee for this prize. Now, let us consider how one generation works in this Naukova model. So I write, actually not I, it's Naukova and Giovazzini wrote such type of Lagrangian, which contains 4 fermion interactions. The pair mass for in Lagrangian is absent, and because of its absence, this model possesses 2 invariants. Usual gauge invariance, which leads to conservation of vector current, and the so-called chiral invariance, which leads to conservation of current. Actually, this symmetry doesn't allow to generate mass in perturbation theory. If you start perturbation theory, you cannot generate, and mass generation occurs only beyond the perturbation theory. The simplest approximation to look at this phenomenon is so-called Hartree-Fock equation, which is full inverse propagator. Here we have full propagator, and here inverse square propagator where mass is 0. How it leads to mass generation? So equation is very simple. It's very simple. You can just integrate, introduce some cutoff, interval cutoff we need it because model is non-renormalizable. And actually, if we consider this model as some effective one, it will be some physical parameter which can be taken from experiment. For example, when you discuss model applied to quarks. And non-trivial solution exists if coupling constants exceed some critical one. It's easily seen to this graph because this graph goes in such way, this line, and you need some G in order to cross this line, this curve, G greater than critical one. So in this case, you get non-periodic condensate, and chiral symmetry is spontaneously broken. What is the reason for this critical coupling? This is because density of set behaves as E square for massless particle and vanishes the energy as a level energy equals 0. I would like to say that actually this Naukova model now occupies a similar place in particle physics as famous Hammer model in condensed matter physics. Now, let's look at quantum electrodynamics, which this phenomenon for pairing of electron-positron we studied long ago. So we solve Weber-Salpeter equation. This is Keldon. So this is equation for the wave function, and you find here moment P is Euclidean moment. So you find the solution for bound states with P square is in Minkowski space that you have tachyon, so instability. This is the same situation. For example, if you find this such kind of consideration in the book by Schrieffer applying to superconductivity. So the presence of tachyon means instability of massless phase. Massless phase looks as this instability arises when coupling exceeds some critical one, which is this approximation is pi over 3. So we have a similar situation as in Abujan-Lazino model. Now, what about real ground state? So you can write down a finger Dyson equation for fermion propagator. Here a general form for this propagator. D is the mass function, and this equation for mass function is non-linear one. It was studied extensively in 70s, 80s by several groups, including Moscow Nobel Prize laureate, and our group. What was found that indeed solution for the mass exists if coupling is larger than some critical one. So there is some threshold for coupling constants. So this solution combines two features present already in Abujan. First is non-analytical dependence on coupling constants. It's of course this dependence is a bit different, but nevertheless non-analytical behavior. It's interesting that in 80s it was thought that maybe in real quantum electrodynamics we have two phases, physical different phases. One is phase with big coupling, which we usually apply, and another one with the first phase at strong coupling. And there were several experiments trying to find this strong, so-called strong coupling phase of QCD experiments performed in Darmstadt. And you can find their description in this paper. But experiments were not very convincing. Until now, we don't know about such phenomenon, whether it's really realized in nature or not. It reminds the situation with so-called positron creation in the field of charge, which Coulomb center with large charge. In QED, we don't find such phenomenon because, first of all, of course, critical coupling required for such phenomenon is rather large. Was estimated in the 70s as 170, so we don't have such nucleus with such charge. But in principle, you can perform experiment utilizing some heavy ions, so to reach this large charge for some short time. When you have large Coulomb center, how your levels, energy levels, they change with growing the charge. So when your lowest level reaches the lower continuum, if this level, if it's empty, then you have spontaneous creation of pair electron-positron, and you can catch positron. Actually, this phenomenon was never observed in QED also, because very hard experiments, but we know that this idea was applied in graphene. For example, this Filter, who are present here, considered it graphene. In graphene, this phenomenon was observed. Now, I come to Landau levels to introduce magnetic field. How magnetic field alters this phenomenon of mass generation. Actually, Landau level of were invented in 1930, but it's interesting that independently, Bronstein and Frank also found this Landau spectra as number of levels before were found for Dirac equation by Rabi 2 years earlier. 2 years earlier, you know this spectrum. But at that time, people had doubts about the existence of these negative energy solutions, and because of that, Bronstein and Frankel decided to solve Schrödinger equation instead of Dirac equation. And they found independently from Landau the existence of such kind of levels. In two-dimensional case, for example, graphene spectrum is simplified, so these two terms are absent. And energy scale, which we have here, characterizes the distance between the Landau level, is given by this formula, and because of this large Landau scale, actually, this is the reason why we observe quantum effect in graphene at room temperature. Now, let's apply magnetic field to Nabuchin-Lazini model. This is just how green function is modified in the presence of magnetic field. Just expansion over Landau levels. And the Kepler equation also is modified. And it's easy to see that if I look at the solution at small coupling G, I found a solution at any small coupling, What is the reason for that? The reason that, in fact, magnetic field reveals density of states. So we say that at zero energy we have zero density of states. Here, Landau levels with zero Landau levels have non-trivial density. Non-trivial density. This is density of Landau levels which enters the formula. This formula. So you see complete analogy with series of conductivity. Of course, here we have only pairing of particles with negative charges, negative and positive charges, so-called excitons, in fact. neutral particle. To see that even the zero Naukova level plays indeed essential role in this phenomenon, we just leave in that equation contribution from zeroth Landau level. Equation is simplified, very simplified, and indeed we find the same formula with very small deviations from it. The reasons which we, the lessons which we extract from this consideration is the following. Why we have one generation small tau? Several reasons. First of all, magnetic field makes a so-called dimensional reduction in the dynamic of reducing fermions. It plays the same role as, in fact, as chemical potential in series of conductivity, because in that case you have dimensional reduction for 1 plus 1 dynamics. One is time, and another one, for example, it describes the motion perpendicular to Fermi surfaces. The second lesson from this is the very essential role of the last Landau level. And non-analytical dependence on the complex. The last thing depends on dimensionality of the model which we consider. Just we see later that this analytical, non-analytical dependence changes to an analytical one in case of 2 plus 1 dimension. Here we see how Landau levels reveals the density of state. So we have some peaks describing Landau levels. But here it's more general, several solutions for several complex constants for this non-homogeneous model. Just illustrating general case, not only for the lowest level. So it seems that solution exists at any complex constant. Now let us make some dimension reduction, so we consider non-homogeneous model in space dimensions 2 instead of 3. The same approximation is easy to solve the same equation, which is now has 3-dimensional momentum integration, and we also find the existence of critical tau. Now apply magnetic field and using the lowest Landau level approximation. Equation turns into such form, and we easily find the non-trivial solution which exists at any complex constant. So, because dimensional reduction is 2 plus 1 to 0, 0 plus 1, so 9. So the mass in this case is function, analytical function. So this is effect of lower dimension. In QED, if we repeat also the same approximation for mass function, but we include also the magnetic field, this equation was transformed into the problem form. Can be a solution for this equation also at any small count. No critical count. What's interesting is that if we switch on critical temperature so that we have possibility to increase temperature and restore symmetry. Then we obtain some kind of phase diagram where critical temperature behaves like square root of B. This phenomenon was also studied in QCD, so quantum Crompton-Mains calculation on the lattice. And at large magnetic field, Big Lock observes this magnetic catalysis. So critical temperature behaves as square root of B. But here's also some region where it behaves in opposite way. And this phenomenon was called inverse magnetic catalysis or delayed magnetic catalysis. So at the moment there is no clear explanation of this phenomenon, inverse magnetic catalysis. At least some probable explanation of it is that coupling constant quantum dynamics will depend on magnetic field too when produce such kind of effects. Now I come to graphene. This graphene lattice composed of carbon atoms is well known. Hamiltonian is known. You have such dispersion relation where we have 6 points where upper conduction band intersects with valence band. And you know that only 2 points called K points are independent. Here it's Hamiltonian. But what I would like to bring, some attention to this picture because look at graphene. What you start from? You start from just a plane of carbon atoms, which you cannot differentiate between these atoms. They all the same. But now, due to translation and rotation events, we know that we have 2 atoms in cell, only 2. And then if we look at here also 2 sublattices because of 2 atoms in cell. And now if we linearize the special law near these points, we have really new quantum number called Valeriy. So K points are Valeriy. You have origin of 2 quantum numbers, pseudo-spin sublattices, and Valeriy also. And besides this Hamiltonian also corresponding to Lagrangian possesses low energy relativistic-like symmetry. So we have new effective symmetry. And for example, if you take a large momentum so that you can go from one K point to another one, this situation reminds us about so-called unified theory in particle physics, because now we have a theory which is described by H fields, which have symmetries SU3, SU2, and U1. So color, strong interaction, big interaction, and electromagnetic interaction. You don't have in your Lagrangian just direct interaction between quark and leptons. But then people tried to combine this so-called standard model, bigger model, which combines slice all the symmetry into one group. Say, for example, SU5. In that case, in this model, you have already interaction which transform quartz to leptons. So, it reminds just this situation with in graphene at large transfer momentum. So maybe in particle theory we should think about some more interesting situation in unified theory underlying standard model. This is very known, so I will brief here. So you can linearize your Hamiltonian near this K point. You have spinor, 2 by 2 matrices, and K point, combine K point and sublattice spinor into 4 by 4 matrices. They come actually to a real Dirac theory, but of course there is no real spin. Real spin here is considered as, for example, Flavin standard model. This first was obtained by Seviano in Central many years ago. QED form, we add interaction between Coulomb interaction between particles, and we obtain such kind of pressure. First properly written papers by Patient and our paper. This Lagrangian possesses very big symmetry, U4 symmetry, generation of this symmetry. And graphene, fine structure constant composed from E. It's equal E square divided over H bar. And here we have instead of the velocity of light, we have the Fermi velocity because of that. Sampling constant is big in free graphene. We have strong interaction between electron and holes in freestanding graphene. Of course, if you put graphene on substrate, where we have the later constant, alpha will be much smaller. Another point, another connection is between condensed matter physics and what people is doing now in high energy physics. They study different kinds of model which present our world as some brane in world which has high dimensions. So we have some kind of branes. Actually, graphene can be considered from this point of view. So if you write interaction of electromagnetic field with particles which live on the plane, here delta Z, you can integrate over Z, and then we come to non-local interaction of quasi-particles in plane. Actually, this kind of, you see, instead of standard form of F square, you have here a non-local form. It is really needed in order to keep Coulomb interaction 1 over R in plane. Because if you consider simply F square, model with F square in 2 plus 1, you get logarithmic potential. Now, how generation happens in graphene. This is the gap obtained in the allowance approximation, but instead of number generalizing model, of course, we have the gap depends on the momentum. So gap is not simply constant, but depends on momentum. And this equation can be solved. Some layers are here close for several couplings. But what's non-trivial is that the solution for this equation, non-trivial solution, exists again if coupling is large, some critical one. This approximation, this approximation which is was taken here is just projection function was taken as a static one. It's a static one. Then we get such kind of solution, which reminds you of the formula from four-dimensional quantum electromagnetics. So, in principle, graphene could be its strong coupling phase could be an insulator. Of course, we know that it's not so, but nonetheless, let us proceed further. So, if we include dependence on the frequency, position function takes this follow form, and frequency coupling becomes a little bit smaller. Several Monte Carlo simulations were performed for graphene and gave critical coupling close to this value. So I would like to mention these papers, so on, like that. In the real graphene, you actually have a situation when coupling actually is less than critical one because Fermi velocity depends on momentum, and at small momentum, Fermi velocity becomes bigger, and coupling constant is larger. So this is maybe real explanation why we don't have gap generation in graphene. So this model for graphene can be generalized to include some four fermion couplings. So it can be called this Гач-Набу-Железинин model for graphene. So we have some changes in the equation, and instead of 1 point, we get such phase diagram. This line separates phase with broken symmetry and phase with symmetry as a result. This analytical expression for this critical curve can obtain. Moreover, several critical indices can be calculated when we cross this critical curve. I roll down here and synthesis that they all satisfy this critical exponent, satisfy so-called hyperscalar relations for t equal 3. And actually, what this model gives, these critical coupling are very close to those found in Monte Carlo simulation. Now, modification of spectrum, graphene spectrum due to Landau levels. Here it's without magnetic field, without gap. Here chemical potential. Now let us, magnetic field is still zero, but introduce a gap. So we have this situation. And now non-trivial magnetic field. We have discrete levels. What is essential that the lowest levels is present for 1 point, K point, and here is absent, and for holes present here but not here. So if we combine two spectrum, we find that the generosity of all Landau levels is for n greater or equal 1 is twice bigger than for zero landau level. Actually, this is also a reason for quantum Hall effect as we know. Now, in QED, in graphene, which is very close to QED model, for landau, the lowest landau level, the equation has also a simple form that can be easily found as gravity generated again at any small tau in proportion to square root of just a figure of when we take into account the gap as a function of landau level. So we included, for example, polarization function, which also depends on magnetic field. So we get this picture how gap depends on landau levels. Now this gap generation can be applied to explain some experiments. Theoretically, for example, if we start from the situation when we don't have gap, then we have all levels are fourfold degenerates and Hall effect which contains these numbers, plus minus 2, plus minus 6, and so on. Now, if we have gaps, then we have the lowest landau, zeroth landau level squeeze, and the corresponding numbers, hidden numbers, contain now 0. So 0. Proceeding further, when we have only Zeeman field without magnetic field, all levels in speed are split in speed. You have such kind of feeling. And last situation when we have both Zeeman field and gap, you get such kind of feelings. So you have 0, plus 1, 1, plus minus 1, and so on. And this actually, these feelings were observed in an experiment by Valeriy Gusynin. This last point, very short about bilayer graphene without magnetic field. This is Hamiltonian for the lowest extensions, which have quadratic form dependence on the momentum. When using polarization function, we must use it in this case. And again, a very nice approximation analytical was proposed by Naukova and Davidov. They got the gap generated at area coupling here, such if we include now magnetic field, electric and magnetic field, we have some kind of phase diagram, which is much discussed now in literature. At large magnetic field, the situation more or less clearer, but still questions about what is real ground state for small electric and magnetic field. Here I write down expression for gaps, how it depends on magnetic field. Actually, it depends linearly, and the critical. This critical line, this black line, this critical line, our electric field and magnetic field. This line separates two phases. Okay, thank you.
When you were talking about the three-dimensional, 3 + 1 dimensional Gusynin, that you had a critical, and then you put a magnetic field on, you get a critical temperature. There was a parameter nu zero. What was that parameter nu zero?
Nu zero?
Nu sub-zero.
It's density of states at 0 lambda.
So it's proportional. So it depends on the magnetic field, is that point?
Yes.
Okay, so there's actually a magnetic field hidden in that formula. Yeah.
Okay, so let's continue.